Christos, for letting me move my talk. I couldn't come because there were some movers moving our stuff. Okay, so I'm going to talk about metatheorems for dynamic weighted matching. So I need to tell you what all these words mean. Oh, even better. Now you can hear me. Is it better?
Yes.
Okay. Matching. A matching, as you all know, is a set of no disjoint edges in a graph. There's two studied problems in this case. So there's a maximum cardinality matching where you're given a graph and you want to find a matching on the maximum number of edges. And there's the weighted matching problem where you also have edge weights. Let's say they're integers and you want to find a matching that maximizes the total sum of the edge weights. Now, we have these classical algorithms that have gotten better and better. For the maximum cardinality matching, we have a node algorithm that runs in m root n time. Then also in n to the omega, where omega is the matrix multiplication exponent. And for bipartite graphs, we have even faster algorithms. For the weighted case, it's a little bit more complicated. Here we also have a dependence on the maximum edge weight, which I'll denote by capital N in this talk. So here we have a log of n dependence, and you kind of need this because you need to read the edge weights. This is kind of weird. If you want to run matrix multiplication, then you actually pay a pseudo-polynomial factor. No one knows how to get rid of this. Now, what I'm going to talk about today is actually the dynamic version of the matching problem. Here, not only do you want to compute the problem, but you want to be able to support updates. Someone comes in and says, this edge is no longer there, or now I'm adding this new edge. What's the new matching in the graph? And here, the situation is much worse. So I'm just going to focus on the update time, assume I'm storing an explicit matching. Here, there's two results by Sankovsky from 2007 for the maximum cardinality matching case. He can perform updates in n to the 1.495 time, which is a little bit better than the trivial n squared time, which you would get via augmenting paths. And in the maximum weight case, you pay this horrible factor over here. Again, we don't know how to get rid of it. Okay, so you may ask, where is this 1.495 coming from? It comes from matrix multiplication. And it turns out that in a certain sense, matrix multiplication is necessary. So we were able to show something like this. You can actually reduce Boolean matrix multiplication to dynamic matching, even in the maximum cardinality case, and even when the graph is bipartite. So in a certain sense, in this, for dynamic exact matching, you need matrix multiplication. So now the question is, what if I don't want an exact matching? So what if I want an approximate matching? So here, the situation is much, much better. So now, instead of maintaining an exact matching, I want just a matching whose quality is just 1 over a fraction of the actual quality of the matching. And so here's what's known here. For the maximum cardinality matching, we have like many, many, many results. For example, if you allow randomization and amortization, you can actually perform updates in logarithmic time. And recently, and get a 2 approximation. If you want a 2 plus epsilon approximation, you can get rid of the randomization and also get worst case. So we really have a lot of results for maximum cardinality matching. For the weighted case, it's worse. For the weighted case, there's only 2 results known. For when you want to maintain an approximate maximum weight matching, there's a 4.911 approximation algorithm that is randomized, so it's expected and it's amortized, and the runtime is roughly like this, log n, just like in the 2 approximation case, but you pay a log n, the log of the maximum edge weight portion over here. There's a second one, which is the analog of this one over here. You can get a 1 plus epsilon approximation in root m over some dependence on epsilon times this log of n factor. So there's only these 2 results, and immediately 2 questions arise. Do you actually need randomization to get a constant factor approximation? Do you need root n time to get something like this. Anyway, and in general, why do we have so little knowledge of the maximum weight matching, whereas we know so much more about the cardinality case? And the two natural questions that we asked was, suppose I wanted a constant factor approximation for the maximum weight matching, and I didn't want to use randomization, because randomization actually for the dynamic problems is very, very restrictive, because it assumes that your adversary does not see your random bits. So I want to get rid of this. So suppose I want the deterministic update time, can I get it less than root n time? We can even do polylog for maximum cardinality matching. We didn't know how to do this for the weighted case. And second, is this log of the maximum edge weight necessary? If we want to solve the problem exactly, it is necessary. You have to read the numbers. Okay, so they have log n bits, so you have to do it. But here, I'm just asking for an approximation. And why should I have to read all the bits in the input? Okay, so I don't really, can I replace this log of the largest edge weight with something smaller, like log n or inverse Ackermann or whatever your favorite function is? Okay, so here's our answer. If you give me your amazing maximum cardinality matching algorithm that has update time, so it's dynamic, it's update time t, that's a function of the number of edges and nodes, then I can immediately convert it into one for maximum weight matching. The approximation factor doubles roughly, so you can set epsilon to be as small as you want, and the update time is within a polylog of this time. You only pay log of the largest edge weight instead of log. Also, nicely, if this update time were deterministic, so is this one. If this one's amortized or worst case, this is also worst case or amortized depending on what it is. Also, because the way this reduction works, we actually only look at subgraphs of the original graph. So if your graph is from some special graph class, it also applies here, and so on. So it's a nice little reduction. So what I'm going to do now is I don't have time to prove anything, so I'll just give you a bunch of pictures and some intuition. Okay? Okay, so what's good about this? Well, we had all these results about maximum cardinality matching. We plugged them in. And now we get the best known algorithms for maximum weight matching in the dynamic case, just immediately. You just plug them in, and that's what you get. For example, you get an almost 4 approximation in polylog n time with some log dependence on the largest edge weight. C is the ratio between the largest and smallest edge weight, and so on. Okay, so what's the main idea? So we looked at this algorithm by Crouch and Stubbs from 2014 that is from the streaming community. So they had a streaming algorithm that gave a 4 approximate maximum weight matching. And then we noticed that actually so what it was doing a bunch of these maximo matchings. And so we noticed that instead of maximo matching, if you plug in an alpha approximation or an A approximate matching, then you would get a 2 A approximate matching here times 1 plus epsilon. And then what we notice is that you can actually make it dynamic. So I'll show you some pictures about how to do that. So here's the main idea. What you're going to do is you take the edge weight range that's between some L and N, let's say they're integers, and what you're going to do is going to split it into these buckets, where each bucket range gets multiplied by 1 plus epsilon each time. And then you're going to take the union of the top so many buckets. And that will be an edge range that I call Z sub I. Z sub I is between L times 1 plus epsilon to the I and the largest edge weight N. And then what you're going to do is you're going to create unweighted graphs that are only composed of the edges with weights within that Z sub I. So there are these included. So the graph Z sub 0 will contain all the edges of the original graph, and the top one will only contain the largest edges. And then in each of these graphs, you create a maximum cardinality matching. We're using your favorite algorithm. And then what you will do, you take the maximum cardinality matches in each of these classes, and then you greedily merge them. So what that means is you kind of start from the largest edge weight class, and you start adding edges as long as their edge points are free. And you go from the largest edge weights down to the lowest. And it turns out that that works. Okay? And so what we do is we simulate this using in a dynamic way. So let me give you an example of this. Okay? So here, do I have time? Time?
Not really.
Okay, so I'm going to skip. So let me tell you how we do it. All right, so this is the main idea. When an edge is updated, we update all the matchings for all the weight classes, and then this will only cost us this much time because the number of weight classes is log n over epsilon, and this T of mn is the update time of the maximum cardinality matching algorithm. And then we show that to propagate these changes, you only cause a log n over epsilon number of changes per change in the original graph, in each of the matchings. And this will give us the following. It will give us that T of mn update time for an alpha MCM implies this runtime for an 2 alpha. And maximum weight matching. Now, this has a log n factor, and in order to get rid of it, we do some data structure tricks that I absolutely have no time for. And that's it. Thank you.
Any questions for David?
Is there a chance to replace the dependence on n by the dependence on the approximation ratio? Or it's hopeless?
On the largest edge weight, I'm not sure how to do that. It's a great question, but I don't know.